Today we're going to talk about a chemical that's basically the hidden foundation of our entire world, but most of us will never even see it. They call it the king of chemicals, and trust me, it has earned that title. So let me start by asking you something. What do a car battery, a bag of fertilizer, and a sheet of paper all have in common? I mean, they seem completely unrelated, right? But what if I told you there's a single, powerful, kind of secret chemical that links them all?
That's right. The answer is sulfuric acid. It's this invisible thread that weaves through pretty much everything we use every single day. And it's not a bit player. It's one of the most important chemicals we manufacture on the entire planet.
So what exactly is this stuff? Well, chemically, it's H2SO4. But way back when, it had this awesome, almost alchemical name, oil of vitriol. How cool is that? But don't let the fancy old name fool you. We're talking about a dense, corrosive, oily liquid that is an absolute heavyweight in the industrial world. So, you might be wondering, how do we make a chemical titan like this? You can't just dig it out of the ground. No, it has to be manufactured on a truly massive scale, and for that, we use a really clever method called the contact process. And here it is, the whole shebang in one diagram. Yeah, it looks a little intimidating, right? You've got burners, purifiers, all sorts of towers, a lot going on. But the basic idea is actually pretty simple. You put raw materials in one end, and you get pure concentrated sulfuric acid out the other. So, let's walk through it. The whole thing really boils down to four main steps. First, you've got to make sulfur dioxide gas. Usually, that's as simple as just burning sulfur. Second, you have to get that gas super pure. Third, and this is the really crucial stage, you convert that gas into something called sulfur trioxide. And then finally, you absorb that new gas to make the acid itself. Now that third step, that's the heart of the entire operation. I mean, the whole massive factory is basically built around making this one single reaction happen perfectly. If you can nail this part, the whole process is efficient and profitable. It's that important. And just like any good recipe, the conditions have to be absolutely perfect. We're talking a temperature between 450 and 500 degrees Celsius. The pressure is actually pretty low, only about 1 or 2 times normal atmospheric pressure. And the secret ingredient that makes it all happen fast enough? A catalyst called vanadium pentoxide.
And that temperature is a really delicate balancing act. It's a total Goldilocks situation. Not too hot, not too cold. If you go too cold, the reaction just crawls along at a snail's pace. But if you crank the heat up too much, the reaction actually starts going backwards, breaking down the very thing you're trying to make. So that little window between 450 and 500 degrees is the sweet spot. Just right.
Okay, so that's how we make it. But the really interesting part is, what can it do? Why is it the king of chemicals? Well, it turns out sulfuric acid is like a chemical Swiss Army knife. It has 3 very different personalities that make it insanely useful. Talent number 1 is the one you probably remember from science class. It's a classic textbook strong acid. You know, when you dilute it with water, it does all the standard acid stuff. Fizzes with metals, neutralizes bases to form salt and water. This is its day job, its most common personality. But that's just when it's watered down. When it's concentrated, oh, it's a completely different beast. It unleashes its second talent. It becomes a seriously powerful oxidizing agent. This means it gets really aggressive and can rip electrons away from other substances. It's so strong it can even go after things like carbon and copper, stuff that most other acids won't touch. And that brings us to its third and honestly its most dramatic talent. Concentrated sulfuric acid is incredibly thirsty for water. I mean, it has such a powerful attraction to it that it doesn't just absorb water from the air. It can literally tear the elements of water, hydrogen and oxygen, right out of the structure of other molecules. And you have to see this to believe it. When you pour concentrated sulfuric acid on something like plain old table sugar, what happens is wild. It doesn't just dissolve it, it violently dehydrates it. It rips those H2O molecules right out, and what's left behind is this growing, steaming black pillar of pure carbon. It's one of the coolest chemical demonstrations out there. And that incredible aggressive power to pull out water, well, that's exactly what makes it so dangerous to handle. It demands serious respect. Because what it does to sugar, it will do to skin and tissue, causing devastating chemical burns. Which brings us to probably the most important safety rule in any chemistry lab. Do as you oughta, add acid to water. You always add the acid to the water slowly, never ever the other way around. Why?
because if you dump water into the heavy acid, the water sits on top, and the heat generated is so intense it can instantly boil, splashing concentrated acid everywhere. All right, so we know how it's made, and we've seen its crazy chemical talents. But let's bring it all back home. Why should you care? Where does this industrial giant actually impact your life?
You know, there's a saying that you can judge a country's industrial power by how much sulfuric acid it produces, and when you look at its uses, you can totally see why. It's absolutely fundamental. We're talking fertilizers that grow our food, paints and pigments, fibers for clothes, other chemicals, you name it.
Let's get even more specific. Think about this. The battery that starts your car, that's a lead-acid battery, filled with sulfuric acid. The rayon in some clothes? Yep, used in the process. The detergent you use for laundry? It's often in there too. It's even used in refining petroleum to make the gasoline for your car.
So you see, even though most of us will never actually hold a bottle of it, its fingerprints are everywhere. It's that unique triple threat of properties, strong acid, powerful oxidizer, and aggressive dehydrator, that makes it the undisputed king of chemicals, the ultimate workhorse quietly building the world all around us.
But all this leaves us with the big, forward-looking question. Making this chemical is a massive, energy-hungry process. So as we all try to move towards a greener, more sustainable future, what happens to the king? What's its next chapter? How will the role of this incredibly important chemical change in the years to come?